All right, well, it's 1 o'clock, and I wanted to introduce our next Stormwater Awareness Week workshop. And it's Kyla Wood. She is the Director of Research and Development with Applied Polymer Systems, Inc. And she's here to talk about a subject that is, well, it's new to the construction general permit, but it's not new to the industry, and that's passive treatment. And her title entitled "The Power of Polyacrylamide." So, Kyla, why don't you introduce yourself to everybody, and the session is all yours.
Sure. All right. Thanks so much, John. And thank you everyone who is joining us today. This is my first Stormwater Awareness Week, so I'm really excited to be participating in this event. As John said, my name is Kyla. I'm with Applied Polymer Systems. Our company has been doing passive treatment with PAM for over 25 years now. And my job at Applied Polymer Systems, I'm a technical director. And so I do a lot of research, training, and things of that nature. So I'm going to go ahead and get started because I have a lot of material I want to cover, lots to talk about. And I think John's going to give me potentially a few questions as we go, but for the most part, we'll save a few minutes and answer some questions at the end. So what we're going to be talking about today is, of course, polyacrylamide with a focus on passive treatment. And so passive treatment, again, it's not a new thing. We've been doing it for decades in a lot of other states, but really excited now that California is adding this really cost-effective and effective tool to their toolbox. So we're going to go ahead and do a flocculant introduction and talk a little bit about PAM or polyacrylamide. We'll briefly talk about passive treatment, talk about how to select a safe and effective flocculant or PAM for our passive treatment applications. We'll go through a couple of common applications, and then we'll bring it all together with a couple of case studies. So first of all, why do we use flocculants like PAMs in the first place? Well, that's because a lot of our traditional BMPs are not able to remove silts and clays and metals and these very small, difficult to remove contaminants because they'll move right through our physical things like silt fence and check dams and things like that. When those silts and clays and metals reach our water resources, it can have a direct harm for aquatic life and also have an impact on habitat. There's a lot of other consequences of sedimentation, but those are two that we focus on a lot. So the solution to these difficult contaminants is to enhance our existing sediment and erosion and stormwater BMPs with things like flocculants and coagulants, specifically polyacrylamide. So there's a lot of different types of flocculants and coagulants that are available. A lot of them look similar, white, granular, flake, but based on some of their characteristics, we use different ones in different types of applications. So in passive treatment specifically, the most widely used flocculant is PAM or polyacrylamide. And the reason for that is primarily because PAM is very safe for the environment. It has a very low toxicity to fish and other sensitive aquatic organisms in comparison to cationic polymers that are confined to active treatment systems because they have high toxicity. So we use PAM because it's very safe for the environment. And we use PAM because it's very effective. It's this large polymer that we can make in different sizes and charges. And it's able to really effectively bind the things that we like to go after, such as clays and metals and silts. So this is a picture. You can see those big flocks that formed from a colloidal or suspended clay solution. The other benefit of PAM is that it's not a new chemical, it's not a new material. It's been used in researched in a number of different applications for over 70 years now. So polyacrylamide was first developed in the 1950s, and the USDA specifically has done a lot of work with it, mainly since the 1970s. And they've done a lot of different research and a lot of papers to show that it can actually improve crop yield and vegetative growth. It does that by preventing erosion, improving soil structure, improving infiltration of water into the soil, keeping nutrients, microbes, and things like that in place. And all of those benefits combined, they found they were able to use PAM to not just prevent erosion, but actually improve vegetation. In addition to the benefits for erosion control, you can see vegetative establishment in our industry is so beneficial because that's usually our ultimate goal in erosion control. So that's a big benefit. But what we'll be talking about mostly is that it's also really useful for water treatment, and not just construction water or storm water, but it's also been used for drinking water and wastewater treatment across the world since about the 1970s. So the construction and stormwater really started in the early to mid 1990s, and the flock log specifically that we'll talk a little bit or a lot about today, it was actually designed in the early 90s for treatment of metal and TSS from mining operations. So a long history of use and a lot of different uses for polyacrylamide. Few more of those uses that I might not have covered, but again, potable water, wastewater, these are the same materials that we're using for our erosion control and stormwater treatment. They're drinking water grade materials. So, and again, a lot of different uses, potable water, wastewater. In the food industry, soil conditioner, animal feed thickener, pharmaceuticals, cosmetics, mining, mineral processing, pulp and paper production, lots and lots of different uses, many of which you can see are in contact with our skin or our food or things like that. So the safety of PAM and its non-toxic properties is what makes it so versatile and how we can use it in so many different ways. So there's different forms of PAM. PAM is a powder or granular form we typically use for erosion control and water treatment, and that's the 700 series silt stop. We have the block log or gel form, which is specifically designed for passive water treatment, and that would be the flock log or the pond log. There's also concentrated liquid emulsions that are often used for erosion control, dust control. They are limited sometimes in water treatment, but I know in California and many other places, we're not allowed to use those for water treatment, not because of the PAM, but because of the surfactants and the emulsifiers and things like that that are used to create that concentrated liquid. It has some toxicity, so we don't use those, especially our company, for water treatment specifically because of that nature. So what we'll be talking about today is for passive treatment is really focused on that granular silt stop or the block flock log. So how does polyacrylamide work? So polymer dissolves in water. This white granular will unwind into this very long polymer chain that's then able to bind through a number of different physical and chemical means to soils, metal, and other particles and form these bigger flocks or agglomerations. For erosion control, it works by holding those particles in place so that they're not mobilized in flows. And for water treatment, again, that same process forms those really large flocks that can then settle out by gravity or be captured now that they're larger by our physical sediment control BMPs. And I'll just show a quick picture here. Again, it's, I like to say it's all about the agglomeration, but basically it's going to be in flowing, moving water. It's kind of a two-step process. The polymer will first, once the water flows over and around the granular or the log, it's going to dissolve, unwind, and then with more water movement, there's a snowball effect where the polymer is going to bind to those sediments, continue contacting more and more sediments, forming these larger flocks or particles that can then rapidly settle those particles that normally, there's some colloidal clays that will sit for weeks or longer without settling and again move right through our physical BMPs. So with in very short period of time using the right type of PAM, we can almost instantaneously form those flocks so they're big enough so that we can improve that water quality and decrease that turbidity. So passive treatment specifically, we can talk about, we do a lot of erosion control. I'm going to focus mainly on passive treatment, but there are land applied applications of the PAM for erosion control when we apply it to water, either to our existing BMPs in swales or concentrated flows, or as a log form into a concentrated flows, then that's where we start to consider that as a passive water treatment application. So really what passive treatment means, it's It has the same goal as active treatment, if any of you are familiar with that. And essentially what we're doing is we're using these polyacrylamides to treat and remove sediment, metals, and other contaminants from water. The benefit is that we don't need computerized systems, filters. Many times we don't even need power. So it's a lower cost, lower energy, and lower maintenance system than active treatment systems. We can still pump the water if we need to move the water around the site. That's still considered passive. And a lot of times we'll use existing BMPs to enhance them in these passive water treatment applications. So the benefits of the anionic of the floc logs, which again were designed specifically for passive treatment nearly 30 years ago. You know, one log can treat upwards of 1 to 2 million gallons of water before it's fully dissolved. They release a relatively steady dose of polymer. There's no injection or manual inputs that are needed. They're safe for aquatic organisms. They're non-hazardous. They're safe and easy to handle. They work in a wide range of temperature. They work a little slower and colder temperatures, so something to keep in mind in the planning process. They work in a wide range of pH, and then unlike you know, some of the aluminum-based coagulants, they don't change the pH. They're neutral in solution. So there's a lot of benefits that for the reason we use these materials specifically for passive treatment. So now that we know what we're using, why we're using it, there are you know, hundreds of different types of PAMs specifically. And so before we do an application, we want to make sure that we're selecting one that's going to be not only effective but also safe. So there's a number of things that we need to pay attention to and that are also required, especially in the California Attachment G. You'll see some of these listed. And when you talk to the manufacturer, you know, we have these things available with the documentation. So you'll be able to, you know, if you ask the right questions, this stuff should just be essentially given to you, so you know what you're using and you know you're using something that's safe and something that's going to work. So first of all, again, we're using an anionic polymer that's safe for fish. It has a very low toxicity. We can use it in these passive treatment systems. We're not using cationic polymers because they're not allowed to be used for passive treatment because of its toxicity. One way to know that we are doing that is that we have toxicity testing that has been done on that product. So if I ask for the toxicity reports, those should be available. The other thing we want to use is a really high grade, high quality PAM. The polymers that we use for our stormwater treatment are the same ones that are used for drinking water. So those polymers will have an NSF standard 60 drinking water certification, so that we know that it's a very pure, high quality polymer. I mentioned the toxicity testing as being something that's important to have available. Essentially, what that looks like is if we get an SDS from a manufacturer, that just summarizes the toxicity information. The manufacturer writes it. So we like to think that everybody out there is honest, but it's always nice to make sure that there is a full toxicity report to back up those numbers, and a company didn't, you know, snag those from another company that spent all the time and money to have those products tested. So, you know, here's an SDS is 1 or 2 lines on this 3-page document. Now a toxicity report where they pulled those numbers from. This is, you know, could be a 10 to 100 page document where they've extensively tested that product, you know, with a couple different species, and make sure we're using something that's safe for aquatic organisms, since we're going to be using it in the open environment. And again, having these reports to back up those products is something that's required by most states as well. So with that, we know that we're using a anionic polyacrylamide. It's been tested, it's a high quality. So now that we know what product we're going to be using and putting out on our site for passive treatment, we also want to make sure that we're following, you know, the fundamentals to make them work effectively. So what I like to call the fundamentals of effective flocculation are using the right formulation. We're using the right amount of the material to be effective. We have enough mixing and reaction time to fully form those flocks so that we can effectively settle or capture those particles. And then last, we want to make sure we're collecting those particles, because our ultimate goal of using any of these BMPs is to prevent turbidity and sediment from moving off site. So once we've formed those flocks, we have to keep them on site along with the polymer that we've used to create those flocks. So we'll go through those briefly here in a little more depth, and then we'll jump into some of the different example so you can see what some of these polymer enhanced BMPs look like before we go into the case studies where we actually see some of those in action. So formulation, again, it's one of those fundamentals to make these materials work effectively. There, as I mentioned, there's hundreds of different types of anionic PAMs. There's different charges, different molecular weights, different sizes. So what we do is we do a very simple kind of screening level test, and we take the soil or water from a site, and we match the specific product to that site soil and water, and make sure that that product is going to react so that it works effectively. If I don't use a site-tested polymer, so if I take 6 of the same water samples and put a different formulation of FlockLog in each of those samples, 3 might work, 3 might do nothing at all. So it's always for the best to test ahead of time, so we're not wasting our time and money, and we're making sure that it's going to work before we put the product out. It's also required by most states, including California, that we do these sample analysis ahead of time as well when we're doing our planning phase for passive treatment. Mixing and reaction, the second, kind of the second and third fundamentals for effective flocculation. When we site match a polymer to our site, we're aiming at having it react and fully form flocks with enough mixing in about 15 to 45 seconds. So it happens very, very quickly. And the benefit for that is that, you know, we're out on a site and we don't have, you know, a contained active treatment system where we can, you know, time our mixing speed and our mixing time and things like that. So we want to make sure it happens very, very quickly, and we don't need a bunch of space to make this reaction happen. So we determine how long it takes to fully form flocks in our sample analysis. It also gives us some valuable information about how much space we need to have this reaction. How big does our flock look based on visible, you know, analysis? Is it going to settle quickly? Do we need maybe some additional particle collection? So, you know, a lot of good information comes from those tests. In addition, once we're out there, if we need to tweak it and get a little bit more mixing, we want our flocks to form in shorter space, we can add rock checks and wattles and baffles. Anything to improve turbulence and mixing and contact time can help us improve our flocculation reaction. So the next thing, dosage, we want to make sure we have enough material. So with the FlockLogs, our goal is for it to be a safe and effective application. An effective application rate is probably less than you might think. So the effective application rate for PAM is usually somewhere between 1 to 10 milligrams per liter, probably on the lower end of that, usually about 2 to 5. So that looks like almost 2 grains of sand in a quart jar. So that's about 2 milligrams per liter. And that's enough to effectively remove, you know, a couple hundred NTUs of turbidity in that quart jar. So a little bit goes a really long way, and using more is not going to make it work better. If you use, you know, more than you need, it's still going to work, but, you know, it's a waste of material. You don't need that much. If you use way too much material, it can actually make it not work as well. So again, our goal is to use as little as we need to be effective. In a real world scenario, what that would look like is, say we're using FlockLogs to dewater a pond. That would be about 3 of those logs fully dissolved, which is about 25 pounds of polymer, into about 1 million gallons of water. And that would be an effective amount of polymer to fully remove 90 to 95+% of that turbidity. So again, a little bit goes a long way. And we gotta, you know, we want to use what we need and need what we use. And again, we're not always recirculating. So when we do a flow through system, the way that we dose that would be based on the flow rate. So typically that would look like for anything under about 800 to 1,000 gallons per minute, we're using 1 FlockLog for 50 to 70 gallons per minute. If we start getting into higher flows, we adjust that rate to kind of get the dosage honed in. But that's kind of a general rule of thumb of how we would do those flow through systems and how we dose them. Again, for soil stabilization and erosion control, I know we're talking about passive treatment, but we also do a lot of sheet flow clarification and a lot of erosion control. So typically when you're using the powders for that, you know, you're somewhere between 10 to 50 pounds per acre, with the most common application rate being about 25 to 30 pounds per acre. And that can, you know, the lifespan of that application is kind of going to depend on, you know, how much it rains and if you've applied with other cover and things of that nature. So the last fundamental before we start looking at some of these different passive treatment BMPs and applications is that particle collection and flock capture. As I mentioned, the goal is to keep that soil and that sediment on site. So, we want to capture those particles. A lot of times we'll do that by using traditional sediment control BMPs and fibrous matting. We really can't get enough jute. I suggest putting jute matting or coconut or hemp or things like that, on your rock checks, in your swales, everything like that, because it's going to be very effective, almost like flypaper, in collecting those flocculated sediment and clay particles. You can see in the upper left-hand corner how fibrous all those that surface area and all those particles that are there for attachment. So these fibrous matting with a lot of surface area work really, really great to capture those flocculated particles. So again, if you can put jute in your entire passive treatment area from beginning to end, I would say do it, because it's very, very effective at improving these applications. So, for our particle collection, you can also use, straw bales, silk fence, again, that jute matting. There's just a lot of different ways that you can collect the particles. Here we had used a tank as kind of a temporary sediment basin, strung jute particle curtains in it to help collect that flock. Just a lot of different ways that we can collect the particulate. You can, of course, just use a basin, settle those particles, let them settle into a basin if you have an area where you can slow the flow and drop those particles out. Here's a temporary basin that was kind of created with kind of like a muscle wall structure. And again, if you don't have a sediment basin, we can use other BMPs. You can also do like a velocity dissipation. This is what I call a dispersion field. So they had their treatment system, and where they discharged their flocculated sediment in their treated water, it slowed down over this dispersion field, collected on that jute matting, and that works really well for particle capture as well. So just a lot of different ways that we can do that. And we'll see a few examples here in a minute. So now what I want to talk about is I want to show some of the common applications for passive treatment, what we like to refer to as our PE BMPs, or polymer enhanced BMPs. This is by no means all of the applications. We have a polymer enhanced best management practice application guide on our website that has, a couple dozen different applications and ways that you can use both the powder and the logs for erosion control, sediment control, and water treatment. So if you want to check out some more of those, that's an option to go look. But what we're going to talk about right now is our basic dewatering channel in both open and closed pipe pump systems. And then we'll go through some of our basic polymer enhanced sediment control devices like rock checks, wattles, basins, and then also look a little bit at sheet flow clarification like polymer enhanced soft armoring and sediment retention barriers. So for our open dewatering channel, again, keeping in mind those fundamentals of effective flocculation, we have flowing water, we have our mixing zone where it's dissolving our logs, flowing over and around them. The polymer enters the water. We continue to have some mixing and reaction time to form those flocks, that snowball effect where they get big enough so we can then capture them on our jute matting or in our basin or on our other sediment control devices. So that's the basic principle of our open dewatering channel. And this is a good example. Auburn does a field day every year, and we always set up a demo. So here we can see those blue logs, or the flock logs. They're introducing sediment and turbid water. It's flowing down the channel. You can see there's a lot of wattles that are included in there. That's helping add turbulence. It also helps collect those flocculated particulates. This particular channel has been treated with both granular form of powder and the flock logs themselves. But this is just a great example. The channel's lined, it has wattles, it has the logs and the powder, and you can see how quickly that water clears as it moves down that channel. So we can have, this was about 500 gallons per minute. So we can do a lot of work in a pretty short period of time with these passive treatment applications. So closed pipe treatment systems, same concept, same fundamentals apply. We need that mixing and reaction and the right dosage and everything like that. But with our closed pipe treatment systems, we're getting all of that done in a closed pipe. So we make the logs into kind of these sausage link or flaps, and we insert them into the pipe systems. And then as the water flows through, it dissolves. We usually have some sort of static mixer inside them. They react, and then we're either, again, using that particle capture on the back end, whether it be a basin or some sort of sediment control structure. People get really creative with these. We make them, but a lot of times we work with other people and they make their own as well. Just really, as long as there's, again, that enough mixing, enough dosage and reaction time, you can create these in a lot of different configurations out of a lot of different materials. The benefit of the pipe systems is if you have high flows or you have space constraints, you don't always have enough space to build big, long, open, linear dewatering channels. So building these pipe systems can be a benefit in those types of situations. So some of the other polymer enhanced BMPs, check dams, wattles, and rock checks and things like that. Those are great options that are often already on site that you can enhance with the PAMs. North Carolina State University does a lot of work with the granular PAM with wattles and rock checks and things like that. So you would just apply the polymer to those BMPs, and you're basically turning those sediment control or filtering devices and kind of supercharging them so that they can remove, we typically aim to get our turbidity below 30 when we do an effective passive treatment application. So we're turning those devices into water clarification devices as well. We also can enhance, again, here's another wattle, and enhanced matting and enhanced wattles with the granular polymer. Again, here you can also do the same thing with the flock log form. I always, if you have a strict turbidity requirement and you want the best results, I typically would add both a granular and a flock log in the same treatment system, and you can, plan for that dosage and everything that you need to do. But here we have the wattles with the logs afterwards. You can see it's kind of in a turbulent area, so that's a good setup for using that BMP as well. Rock checks are another great option. You can see we love that jute matting. So we put the jute matting on there. We apply the granular form of the polymer. So as the water moves through there, it reacts with the polymer. And in addition to dropping out the larger, heavier sediment, we're able to react those particles, form those larger flocks, and actually use this as a clarification device and a particle capture device. Basins, of course, are a great option to use with the flocculants, both the granular and the flock log, because we have usually channelized conveyances that lead into these basins. So we'll put our polymer in those conveyances. We have our channelized flow. We get our treatment. Ideally form our flock in the channels that lead into the basins, and then they settle into the basin. And so it's a great setup and one of the most commonly used polymer enhanced BMPs. The other thing we can do is, again, this it's not necessarily considered a passive treatment application because it's a land applied application, but we often have turbidity sources that aren't coming in channelized flows. So if there are bare soils or sheet flow that's an issue that's causing poor water quality on a site, we can also apply the polymer to existing mattings, which is what is here on the left-hand side. So that's a polymer enhanced soft armoring, which is basically the granular form of the polymer applied to a fibrous matting. So that has two benefits, is that it works for erosion control. So we're stopping bulk soil loss, but it also works for clarification. So if we have fine clays and silts, those can still be mobilized and move from underneath a traditional matting. And so if we use the flocculant, we're able to flocculate those fine particulates. And so we've stopped our erosion, and we've also improved our water quality and clarity as the water moves down slope. Another common, and here's some other examples. You can, we like our fibrous mattings like jute, but you can really apply the powder with any other type of cover and get similar results. So sheet flow clarification, another really common and very effective BMP that's actually been spec'd in a couple of states, is the sediment retention barrier. This is basically 2 rows of silt fence with straw or mulch layered with that site-tested form of the silt stop granular polymer in between. And so as the water moves through, again, that silt fence alone isn't going to take out fine clays. And so as the water moves through and reacts with the polymer, we're able to flocculate out those colloidal clays, form these bigger, larger, heavier flocks. And many of them will either be captured in the straw or mulch or by the second row of silt fence. And it's very, very effective at clarifying water and collecting those flocculated particulates. So we can use it for water treatment. We can also use it for particle collection. So those are some of the really common polymer enhanced BMPs that we can use for passive treatment. And so what I want to do for the kind of second half today is go through 3 different case studies where we've incorporated a number of those BMPs and those different types of PAMs, both the granular and the flock log form. So we'll do an open channel water treatment case study that was done down in Florida in a sediment basin. And then we'll do a closed pipe, basically a pump where we pump the water through a pipe treatment system. And then lastly, we'll do one that was a treatment train where we used a lot of those different BMPs together to treat some water that came from a dredging operation in Tennessee. So the first one is just an example of that very basic open channel water treatment system. These can be flow through applications, or in this case, we went ahead and did a recirculation system. And so what we did here is we had our turbid pond and we created a ditch or a channel that we lined with plastic. Again, we want our channels to be lined because we don't want any extra sources of turbidity coming in after we do our polymer treatment, because it can mask the work that we've been doing. And if we have an unlined channel, that flowing water can also pick up additional turbidity and decrease the clarity of the water. And so we line it with plastic and then we line it with jute matting. We put our flock logs in the system. Again, we dosed that based on our flow rate. I think this was about 300 gallons per minute. So we used 6 flock logs for this application. And then we pump our water down that channel and recirculate it until we've clarified our pond to the point where they could discharge it. Down in Florida, a lot of times that numeric limit is pretty strict depending on where you are. So I think they needed to be below 32 in this specific application. So here was where they did, they constructed the ditch, they just dug it out, lined it with plastic, and then again with that jute matting, and then put the polymer logs. You typically want to put your flock logs in the upper 1/3 to 1/2 of the channel, so closer to the source of the water. And that's just going to give us the more mixing and reaction time that we have as the water flows down the channel, the more time we have to form those flocks. So the more mixing and reaction, the better. So we don't want to put our logs right at the end of the channel where they have, a split second from the time the water hits them and then they discharge into the pond. Because if they're in the pond, that's considered, more of a stagnant, even if there's some slow flow in your pond. It's not going to be enough to form those flocks. So we might get the polymer in the water, but we're not going to fully form flocks. So we want to put our logs upstream in the channel so that we're able to have that 15 to 45 seconds of flowing water after they've contacted the logs to fully form those flocks before they discharge either into our particle capture or into our basin. So again, there's our logs. We've have the channel that's lined, and then we will pump the water over those logs. We also went ahead again, as I mentioned, if we want the lowest clarity, it typically uses a combination of both the logs and the powder. The powder is great for water treatment because it has a lot more surface area, so it can have a little bit quicker results in terms of that flocculation reaction, so it can happen a little bit faster. And so using them together is a really good benefit. So this one, we use both the powders and the logs in the channel. And then we have, I have a video. It's just being slow. Let's see here. Okay, so again, our basic dewatering channel, we're pumping the water out. It's moving over and around the logs. And as it's going over the logs, again, they're dissolving. And then once that dissolved polymer is in the water, we want that mixing and reaction time to form those flocks. So as the water's moving down the channel, that's what's occurring. And once we get to the back end, we're also using that jute matting is collecting some of that particulate. And so ultimately we're settling the flocculated particles in the basin. But if we were to add some wattles and some rock checks and some additional jute, those would capture the majority of the particulate, depending on how much space you have and what your flow is before it even reaches the basin. So there's, again, multiple ways to collect that particulate. But this is kind of the basic steps of an open dewatering channel. And sometimes you're not pumping, sometimes you're working with intermittent stormwater flows. That's very common. So, we can pump the water. We can also, be working with gravity fed flows. So just some of the, with this treatment specifically, the pond was a little over 2 million gallons. And, how quickly we can treat a water body really depends on our pump rate. So we can do applications from a couple hundred gallons per minute to a few thousand gallons per minute or more, as long as, again, we have that enough material, enough mixing and reaction time, and we're collecting those particulates. So this treatment specifically, at about 300 gallons per minute, we pumped for 6 days, and that's about how long it took to fully treat the pond at that flow rate. And we ended up with a final turbidity of less than 10 NTUs. It was actually 8 at the end of this. So really, really effective application using those PAM materials. So the next example is an in-pipe treatment system. So again, this is the same principles, but we're doing that whole flocculation treatment in a closed pipe system and then discharging it into a basin. So this was at a theme park when they were doing the Star Wars attraction. So there was this large sediment basin that they were constructing, that they had during construction. And so it was for the Star Wars project at Hollywood Studios. So we have this large sand mine pit. At one point, they had done an alum treatment that was relatively successful, but then they had a large hurricane come through, stirred all of that particulate up. There was a lot of flooding. They lost containment in the pond, and so they, with the alum, if there's a lot of mixing, it kind of resuspends that. And so they decided to go in and do a PAM treatment to kind of clean that up. And so this pit specifically, it was about over 20 acres and about 30 to 40 feet deep. The turbidity in this pond averaged somewhere between 300 to 400 NTUs and was nearly 300 million gallons. I'm not sure what happened here. Okay, was about 300 million gallons. So again, we use this in-pipe treatment system. Typically, we see pipes anywhere between 4 to 8 inches in diameter, depending on what type of treatment system you're using. And they usually have some sort of static mixer or some sort of change in diameter and some way to get the laminar flow in those systems kind of broken up to get some turbulent mixing. So those are kind of the main components. They also want to make sure that there's enough hose or pipe length to complete that flocculation reaction. Excuse me. So those are the main components in those pipe systems. Usually a single pipe system is not going to do much more than 1,200 gallons per minute. So when we're doing really large flows, what we'll often do is kind of link these systems together and treat higher flow rates. So we've done projects that are, upwards of 10,000 gallons per minute, but you typically be using, multiple of these different treatment systems. So a couple of things to keep in mind is that when we're doing these pipe systems, we still have to get up to dosage. So what we do is, in this, you can see those Y cleanouts, and each of those Ys has a kind of sausage link shape that is inserted in there. And so those are, essentially the same as a same amount of polymer as a regular size flock log, but they're in that sausage link shape. And so you still have to get enough of those in your pipe system to get up to the correct dosage. So the way that you do that is you link multiple of those dosers, as I refer to them, in a line so that we have enough polymer logs on a single flow to get up to enough dosage. So that's, we link those systems together to get up to dosage and to get enough mixing and reaction time. So then we pump the water through those, we get the treatment in the systems, and then we still have to collect the particulate again in some manner. In this system specifically, they used again that modular flock pit, and so they had this constructed again out of kind of plastic barriers, and then they lined that with a plastic lining. And then again, can't get enough jute matting when we're collecting that particulate. They also added some baffles and some of the powder material. Again, this was also in Florida, so we're looking at trying to get below that 32 NTUs, and they were eventually discharging into a wetland area after the particle collection area. So the water goes through the pipe system, through the flock logs, and then into this system, into this particle collection, where we get a little bit more reaction and capture those particulates for a polishing step. Here's just another view of that flock pit, and you can see the Y and the pipe from that pipe system off to the side there. So, and again, all of that jute matting, can't use enough of that for the best results with these passive treatment applications. And again, we can pump in passive treatment applications. That's still considered passive treatment because we're using it to move the water around the site. So here's the water that it's entering into the flock pit, reacting with the polymer, building those flocks, binding on those jute baffles and on the jute that's lining the basin. You can see there's a lot of coloration in the water, and that's just tannins. You can see that it's actually relatively clear. The flock logs aren't going to remove, tannins or humic acids or any of those dissolved organics, but you can see that the water is very clear when it comes out, and it's removed the majority of that sediment. So the final discharge off of this site was again a 12. So we got it, our goal is usually to get it somewhere in the mid 20s or below. And so with this site specifically, from 3 to 400 NTUs down to 12 is about a 97% turbidity reduction. And again, that eventually went through those final sediment control areas, and it was discharged into a wetland. So clean the pond, and that was the finished pond, and just a really successful project with a lot of water moved. So again, really high flows, for extended period of time, ended up doing about 2.3 billion gallons of water in this project, with that final discharge of 12, which was below that target limit of 32. And again, which was about a 97% turbidity reduction. So the last case study that I wanted to go through was in Tennessee. This is the Kentucky Lake dredging, where we used both flock logs and the silt stop powder. And so this project specifically it's a good example because it uses a few of those different basic polymer enhanced BMPs together in what we refer to as a treatment train to get the best results. So Kentucky Lake is the largest man-made lake in the eastern US. Its primary use is flood protection, but obviously lots of different uses for recreation and things of that nature. So a homeowner had a lot of siltation in the cove that they lived on that decreased the capacity and the depth, and they wanted to regain use of that cove. So they had received permission and planned to dredge about 500,000 cubic meters of that accumulated sediment. So the original plan was to send the dredge spoils to a settling pond, which was pictures here. And then from there, they were going to take the overlying water and discharge that through a forested area that was owned by the Tennessee Valley Authority. And the idea was that this was going to work to filter the sediment and slow that flow down and work as a natural filter, so that it would get the sediment out before it discharged back into the lake. They had some pretty high flows that were moving through here, and it actually caused more erosion, and we had higher turbidity that was moving into the lake than when they started in this forested area. So they shut that down pretty quickly, and decided to use this polymer enhanced treatment system to handle that erosion and the turbidity issues. So it was kind of a two-step process where the water went from the spoils basin, went over through the polymer logs in a mixing channel. And then once it went through that open kind of dewatering channel where it went over the flock logs, we sent it through that forested area. But in that forested area, we lined it and turned it into a dispersion field. We lined it with jute matting. We also added some of the granular polymer. And then we had a sediment retention barrier, which, if you recall, is that 2 rows of silt fence with the straw or mulch in between. And we use that as kind of a last line of defense, and a final polishing step before it discharged back into the lake. So this was I think it was about 3,000 gallons per minute that they were treating in this. So they just built this open channel that they made out of straw bales that they lined with plastic. The logs themselves have a internal coconut skeleton that the polymer is molded around, and that has a rope that comes off with a tail that you can stake into channels. In this specific case, they didn't really have the space for that, and it also had pretty high velocity flows, and so they had put them into these milk crates and then tied those off to stakes and trees. And so the logs are actually in those baskets that you can see in this dewatering channel that they constructed. So the water flowed over and around those logs, through the dewatering channel, and then into that dispersion field in that forested area that you can see where the water is discharging into that. So this was our mixing system. The forested area, again, we lined it with that jute matting. We're hoping, and we added some polymer at the front end of that. And so we're hoping to get some more reaction and also to start collecting those flocculated particles. You can see they also added some baffles to help slow the flow down, get some more mixing and reaction. Again, the more mixing and reaction we can get, the better the results are going to be in forming those flocks. So we have the water that's flowing over them, forming those flocks. It's starting to collect on the jute matting. And then at the end of that, again, they didn't use traditional silt fence, but they used some geotextile material again to create that sediment retention barrier. So that's that 2 rows with the jute or with the straw and the mulch in between. And again, that was kind of our polishing step and our last line of defense as it moved through that system. So when it finally went through those 3 different polymer enhanced BMPs, we were discharging water back into the main lake that was lower than background. So very, very effective using those 3 applications together. So just to recap, again, we're using the main steps of doing a passive treatment application is, first of all, knowing what we're using and using something that's safe, anionic, it's been tested, it's drinking water quality. And again, all that information should just be readily available for you when you're ready to do a passive treatment application by asking the manufacturer. You also want to make sure we're using it correctly. So we're using the right form. Is it what type of application or treatment are we doing? What are our goals? Do we need a flock log? Do we need the silt stop? Are we doing erosion control? So we want to use the right form for the correct application. We want to use the right formulation. It must be matched to our specific site and water. We have to have enough mixing and reaction time. And then we also have to capture those particles before the water ultimately leaves our site. And if we do all those things together, then we just get to, reap the benefits of that improved water quality. So I'll just show one more video that I think this was a very small demo that was done at a kind of a university demo in Georgia, but it's pretty dramatic. You can see the flock logs up there, the turbid water is flowing out. It's just a garden hose flow, but you can see how rapidly those flocks can form and attach to, sorry, I didn't keep meaning to turn the sound off here. And so you can see it rapidly binding and collecting on that fibrous jute matting. And so those flocks in this, the reaction can take longer, and obviously with higher flows, it takes a little bit longer to collect those particles. But you can see here how quickly it can happen when we use that site-matched polymer, and how large those flocks are, so that they can be right there, those flocks that get collected, and then we have our clear water moving off the end. So with that, again, I really appreciate you all joining me, and I've got 10 minutes. So if you have any questions, I'd be happy to take them now.
Yeah, Kyla, we do have one question that was in the chat. So does polyacrylamide remove bacteria?
So it does. It does. Actually, some of my I did some, my master's work was on using PAM to remove cyanobacteria. So they actually use it regularly as a material to harvest biofuel from algae. And if you think of bacteria as kind of the same concept, and it's kind of a biocolloid, and so you can use polymers to both prevent microbes and bacteria from being washed out of soil when you're using it for erosion control, and you can also use it to remove bacteria. So the only thing is there are rules for treating algae and treating bacteria, since the PAM is not registered as a for those uses specifically. So it's something to check on. But can it? Yes, it can.
All right, great. And another question. How do we know if the treatment's not appropriate for the soil? I.e., what result or parameter would we be looking for?
So you mean when we're doing the like the site-specific testing?
Yes, I believe that's the context.
Sure. So when we're doing a essentially, if it I have a really good video of the what that looks like when you do it. But basically, if I took a you saw that last video where that flock formed, and then we had that clear water running off. So if I'm doing a site-specific test and against a soil or a water, you'll be able to physically see that flock form, and if it's matched and it works for that soil, then you'll see it react. If it's not going to work for that soil, then you might see nothing happen, to where I can mix it for 5 minutes, but I still have a lot of turbidity. And kind of the same concept if we're doing a test for erosion control, is that it's just a visual kind of observation of whether it reacts. And you can use a turbidity meter and add water to it and kind of measure the before and after turbidity. But it's very dramatic, so a lot of times we'll do these even without a turbidity meter on a tailgate on site, and you'll be able to visibly see which one reacts with the soil and forms those big flocks.
Okay, and I guess just a follow-up question, why would one PAM work and another not? What's going on chemically?
Yeah, so again, they're all those anionic polyacrylamide, so they're all negatively charged polymers. Most soils are mixtures, and a lot of the PAM products are actually mixtures of different anionic PAMs. And so, it's basically the things that are changed on the different formulations is the size of the polymer, the charge density, so kind of how many different charges are on that chain. And so those are the main ones. There's been a lot of different studies that have kind of looked at those different characteristics of a polymer and tried to predict, based on a specific soil type and soil characteristics, can I use this charge density and this molecular weight for this specific soil type? And although there's been a lot of work done and a lot of people have tested that, pretty much all of those studies have come down to that you have to physically get your hands on the soil sample and the polymers and do that jar testing. So there's reasons and there's differences in the polymers, but you still have to physically test them to see which ones are going to be effective.
Okay. Here's another question. How should recovered PAMs and sediment and jute netting be disposed of?
Sure. So it depends on where you are. Again, as I mentioned, the PAM is not a hazardous material. And a lot of times, if you have a jute matting that has both PAM and sediment that it's become saturated with. So if you're doing a a treatment and your PAM or your jute matting becomes saturated with those flocks, you do need to you can just layer more on top of it to keep collecting those particles. Eventually, when you need to dispose of those, again, it's not hazardous, so if it's possible, you can leave them in place because it's biodegradable. You can also dispose of them, however you would otherwise dispose of those sediment control devices. Some states will use the saturated jute that now has PAM and sediment on it, and they'll lay those as an erosion control device on areas of bare site or of bare soil, because now you have PAM treated jute that you can use for erosion control. So depending on your state, if they'll allow you to do that, there's a lot of people that do that as well, kind of repurpose it.
Okay, so you just move it from the channel to a slope.
Sure.
And kind of a follow-up question here. Someone asked if that flock gel, I guess on the jute, can that be remobilized? Under what circumstances might it break free again?
It really, I mean, it shouldn't. Now, if I go out there and if I can scrape it off, it's not permanently on there. But PAM is, once it's bound to sediment, and it wants to be bound to that particulate, and so once it's bound to the sediment, it's very unlikely that it's going to be remobilized. It takes a lot of energy to kind of break those flocks apart. But if I go out there and I scrape the flock off the jute, I can get it off, but for the most part, it's pretty tightly bound on there.
All right, great. I think that's all the questions we have, Kyla. So how can people get a hold of you if they have questions for you about your products or about using passive treatment?
Sorry, should have left that up at the end there. So there's my contact information, my email and my phone number. So you could just take a picture of that, or you can contact me at any of those, and happy to answer any more questions that you might have about the passive treatment or the PAM or anything along those lines. So.
All right. Well, thank you so much. It was a fascinating presentation. In fact, I was just astounded by the volumes of water that were being treated, both in flow rate and just sheer volume. Mm-hmm. And it certainly gave me some ideas as a QSD of things that I definitely want to try on this next wet season. They say it's going to be a wet one, El Nino year, so we probably will have opportunities to try it out. So thank you very much for being a part of Stormwater Awareness Week, and to all our attendees for this workshop. Thank you so much for being a part of this workshop. We have lots more coming up, so hopefully you can take advantage of some more of the free education going on this week at Stormwater Awareness Week. All right, thank you, everyone. We'll see you in the next workshop.
Thanks so much.